You're probably very familiar with the modern periodic table. It's probably something that you were introduced to in grade school. But in the 1700s, of course, there was no periodic table. There were only 15 elements that were known. And it's interesting to ask, where did this come from? How did this evolve? Clearly, it's a very useful table for us now, but back before many elements were discovered, it's not at all clear why this ordering would have come about. Now, by the time we get into the mid-1800s, now we have 50, 60, 70 elements that have been discovered, and there's a real need to organize these elements and to look for correlations. Correlations in physical properties, chemical properties, the mass of the elements. Many different people tried to do this, and a lot of different tables were in fact created, but the most successful table was one created by Dmitri Mendeleev. Now, Mendeleev was an avid card player. In fact, his favorite game was a game of solitaire, a variation of solitaire called Patience. And it occurred to Mendeleev that much in the same way that cards not only can be looked at in order of value of the card, they can be looked at in suits, that it might be possible to arrange the elements based on their atomic weights, analogous to the value of the cards, and to look for some second variable. And the variable he was most interested in would be chemical reactivity, combining ratio specifically. The fact that, for instance, hydrogen combines in a 2-to-1 ratio with oxygen, and other elements combine with oxygen in a 2-to-1 ratio. Perhaps if he tries to correlate those two ideas, that will come up with a table that is useful in predicting unknown elements. So what he literally did was took a series of cards, prepared a series of cards, much the same size as a deck of cards, but the cards were prepared with the elemental symbol of the element, as well as the atomic mass. And he simply laid the cards out based on, or in order of, increasing atomic weight. So I'm just going to do that. We'll just lay these cards out here much the way he would have done. Simply, now I should mention that I don't have as many elements as he had to work with, but this just gives you an idea of the process that he went through. Okay, so there we have it. That's an ordering based on increasing atomic weight. And you'll notice they're different colors. A second thing that he did was he took everything that was that combined with oxygen to make an oxide in a 2-to-1 ratio, for instance, like hydrogen, and colored it the same. So hydrogen, lithium, sodium, potassium, rubidium, all combined with oxygen in a 2-to-1 ratio. Likewise, beryllium, magnesium, and calcium all formed oxides in a 1-to-1 ratio with oxygen. And the same could be said about boron, aluminum, so on. Now, let's take a look at what we have. There clearly is some type of correlation. Notice that this comes as a group of 3, this comes as a group of 3, but it's not a strong correlation yet. But perhaps if we tried to keep our ordering of atomic weight, but also try to better align the colors, we might get a stronger correlation. So let me just move hydrogen up into its own row. That'll match it with lithium, and I'm going to take this row and just slide everything over one. We'll put fluorine back over here and slide it over. I'm still trying to keep the ordering of masses the same, but I'm just changing my break point now. Okay, so we'll take chlorine and move it back over here, slide these guys over. And now this is puzzling. I guess we should put arsenic over here so that we keep it in line with its chemical reactivity. And rubidium we'll have to bring down here, so we'll slide these guys over. Now look at that. Our correlation is now much stronger. We've got all the greens lined up. I've still maintained ordering as far as atomic weight. and everything almost looks perfect. We have a couple guys missing here. That's interesting. And we have these guys that don't quite match as far as chemical reactivity goes. So we'll talk more about that. Let's talk about this for a moment. This suggested to Mendeleev that there might be a couple elements that hadn't been discovered that were members of these two families. And in fact, he went ahead and coined these Eka aluminum for below aluminum and Eka silicon. Now remember, these didn't exist yet, but he postulated that they did exist. I shouldn't say they didn't exist, but they hadn't been discovered. So he postulated that these elements did exist, and furthermore that we could predict certain things about their properties. The combining ratio of Eka aluminum should be the same as the combining ratio for aluminum. Likewise, if carbon or silicon formed in a 2-to-1 ratio with oxygen, Eka silicon should as well. And so, based on their positions of these missing elements, he was able to predict not only information about chemical reactivity with oxides or with chlorides, or as a chloride salt, but also physical properties. The fact that this has probably a melting point that is similar but in between aluminum and indium, and likewise silicon and tin would bracket the melting or boiling points of Eka silicon. So in fact, based on that, what now is known as germanium has properties very similar to those predicted by Mendeleev. You'll notice atomic weight, density, he predicted very close. He knew the melting point was very high. He knew the combining ratio with chloride, with oxygen. So he was able to predict a lot about an element that hadn't even been discovered yet. Likewise, the same thing could be done with Eka aluminum. He knew the combining ratio with oxygen, or could predict the combining ratio with oxygen, the combining ratio with chlorine, although it's not here, atomic weight, density. And so the important point here is, even though these elements, and Eka aluminum is turned out to be what we now know as gallium, even though these elements hadn't been discovered yet, Mendeleev was able to make predictions, very accurate predictions about their properties simply based on their position in the periodic table, or their absence in the positions of the periodic table. So very, very powerful tool. Now what about this problem down here? Notice that these guys are switched. Okay? Well, that still is a mystery. Maybe we should pay more attention to combining ratio. Maybe we should pay more attention to atomic weight. That still wasn't resolved. But in 1897, Ramsay discovered a new element. By distilling air, he discovered the element argon, a component of air. Argon was very puzzling because it didn't come with other elements. Argon was indeed a new element, but didn't form compounds readily with oxygen or chlorine. This was a problem because we didn't know where to put it. He didn't know where to put it in the periodic table. The only value he had for argon, I shouldn't say the only one, he knew about its melting point and boiling point, but he did know about the atomic mass, and based on atomic mass, it suggests that argon should be placed here, somewhere between calcium and potassium. Well, that's interesting. Does that mean if this combines with oxygen in a 2-to-1 ratio, and these guys combine with oxygen in a 1-to-1 ratio, does argon combine with oxygen in a 1.5-to-1 ratio? Maybe. Maybe it's just very reluctant to do so, but maybe that's possible. Maybe there's a missing family here. So if we go ahead and look at, that suggests that we should really slide everything over. So if I go ahead and just move these guys over to make a little bit of room here. Maybe there should be a new family that we just haven't found all the members for. It fits right in between this group and this group. After all, the atomic mass of argon is right in between. Well, sure enough, other members of this family soon were found. There's neon and krypton, other members of the family. But there's a problem with this. They fit in this family in that these guys also were very reluctant to form compounds with other elements. We now know that we can get krypton to form a couple elements, but again, very difficult in general to get these materials to form compounds. But notice the masses don't work now. Neon clearly doesn't fit between sodium and magnesium. It's lighter than sodium, and likewise, krypton is lighter than rubidium. So that suggests that these guys should be over here based on their masses again. So let's go ahead and move these guys out of the way. I'll slide these guys back to where we had it. And again, this is essentially the process that Mendeleev went through. And we'll go ahead and put these compounds, referred to as the noble gases because of their seeming resistance to form compounds, we'll put that all the way out on the end here. Okay? Now, we have a pretty complete picture. We have a little bit of a problem again with these masses, and maybe that suggests that we shouldn't worry about these masses so much either. Well, the other thing that happened at the beginning of the 1900s was two other important things. Rutherford had been studying the nucleus, and we now knew about the notion of atomic number, the number of protons in the nucleus. And Moseley's studies with X-ray emission of elements revealed an important correlation between the frequency of the X-ray emitted and the atomic number, not the atomic weight, of the element. That suggested that what's more important is atomic number, not atomic weight, and given that iodine has one more proton than tellurium, the atomic number is larger, it suggests that these two should be switched around. And that brings them into line as far as their chemical reactivity, as far as their combining ratios. So, summing this all up then, at this stage, it sets the stage for the discovery of many more elements. Again, I haven't shown you all of the elements that were known here. With the transition metals I've left out. That's why there's a big break in the masses right here, okay, between this family and this family. So that suggests that we should open this up and make room for the transition metals. But the process did two important things. It pointed out missing elements and suggested where to look for new elements, and it pointed out flaws in trying to make the wrong correlation. In other words, initially, Mendeleev tried to correlate atomic mass with chemical reactivity, and that turns out to be an incorrect correlation. It's not the atomic mass that's important, it's the atomic number that's important, and by trying to organize the elements into a table, that was made very clear. So, chemists and scientists today use this approach very often. When they collect a bunch of new data about a new system, we try to make sense of it. We try to make tables of that data with the hope that correlations will emerge, and that leads then to valuable new insights between one property and another.